All right, hello again, Year 12 method students. We're going to have a look in this video at the derivatives of sine x and also the derivative of cos x, and again use this sort of graphical approach to try to explore why their derivatives are what they are. And it's quite an intuitive approach, but it's a really good one to think about because we need to understand when we look at graphs, we need to be able to identify things like where is the graph increasing and have a positive gradient, where is it decreasing, have a negative gradient, and where does the gradient of a graph equal zero. So this is kind of bringing together a couple of key skills that we need to have anyway in order to try to understand why certain functions have the derivatives that they have. So here's our graph of y equals sine x, and I've just sketched it for, well, slightly more than one cycle, I suppose. I've kept the axis scales in sort of just whole numbers here rather than putting them in pi or multiples of pi. Mainly so that when we pick our different points and use our tangent lines, we can actually see the gradient more easily. So let's explore the gradient of y equals sine x just over its first cycle, and we're going to do that by drawing a tangent line. Okay, so here's our tangent line, and we can see that as we sort of move through one cycle, we have a positive gradient for a period of the graph, and then we get to a maximum turning point here where for an instant we have a zero gradient, then we have a negative gradient, until we get to this minimum down here where we have zero gradient again, and then gradient starts increasing. So if we start to try to build up some points and actually plot a derivative graph here, well, if we start from 0, 0, the gradient of this tangent line when we draw a tangent at 0, 0 is actually exactly 1. Okay, so when x equals 0, the derivative, the gradient of sine x is 1. Okay, so let's plot that as a point. We can plot the point 0, 1. As we keep moving, and we won't do every single point along the way, but you'll see that as we're moving to the right here, the gradient is getting less and less and less and less until we get to the first maximum here where the gradient becomes 0. Okay, so from x equals 0 to this point here, which we actually know is x equals pi on 2, the gradient has decreased and eventually become 0. So we can plot a point here that says, well, the gradient at pi on 2, because remember what we're plotting here is the derivative graph. So the gradient here is 0. And as we keep moving forward and looking at our tangent line, we now have negative gradient values, and we keep getting sort of negative gradient values. And actually, there's going to be a point in the middle here. If you watch the tangent line really carefully, here we've got a negative gradient. It's getting steeper and steeper and steeper, but there's going to be a point somewhere in the middle where the gradient starts to become a little bit less steep, right? Over here, it's getting less steep again. The steepest negative gradient actually occurs at this point here where x equals pi. It occurs at our x-intercept. And if you look carefully at the gradient of the tangent line at this point, it's actually equal to -1. You can pick 2 points on the line, do a rise over run, and you'll see that the gradient of the tangent line is -1. And so at this point here, when x is equal to pi, the gradient of sine x is equal to -1. And so we can plot that as a point on our derivative graph. Okay, and as we keep moving, we get down to this minimum turning point, which we know is a gradient of 0. And so what we're plotting for our derivative graph is a point on the x-axis because that's representing that the gradient is 0. And if we move through to finish just one cycle of the graph, when we get to x equals 2 pi, which is approximately this point here, our gradient's back to +1 again. Okay, so let's plot that final point. Now, if you look carefully at those green points that we've plotted, and just for now I'm going to get rid of that tangent line so it's out of our way. Those green points that we've plotted form key points of a graph that we know pretty well. And if we actually join them up, and you've got to trust me on this one a little bit, that when we join them up, the bits in between are going to look like this. That's actually the graph of cos of x. So the derivative of the graph of sine of x has given us the graph of cos of x, and that's exactly what happens. The derivative of sine x is actually cos x. And that's a pretty cool feature, right, of sine and cosine graphs. So, and obviously very handy for us when we're asked to differentiate functions of sine x. And so there you go, pretty cool discovery. I'll let you think about that for a second. The derivative of sine x is cos x. And if that wasn't cool enough, well, we're going to do this process one more time to work out what the derivative of cos x is. So now let's imagine that, and I might just get the sine x graph out of the way here. Let's imagine now that we want to find out what's the derivative of cos x going to be. Is it going to come back to sine x, or is it going to be something else? Well, let's have a look. So repeating this process, if we draw a new tangent line for the graph of cos x, and I'm just going to move this tangent line back to 0, 0. Well, let's just do the same thing and see what happens. We might get a similar thing, who knows. So we know that cos actually starts, the graph of cos starts from its maximum, right? So the graph of cos x actually starts up here at 0, 1, but the gradient at that point is 0. So if we were to plot that point, remember that we're now plotting points for the derivative of cos x, that would actually be a point at 0, 0. And as we move our tangent line along to the point where it gets most steep, which is at this intercept here, well, that gradient, again, look carefully at the tangent line, pick 2 points, do a rise over run. That gradient at this instant here is -1. And so we can plot that point to build up a reference of our derivative graph. As we move the tangent line along to this minimum here, where the gradient becomes 0 again, well, we'd now be plotting a point that's back on the x-axis for the derivative of cos x. And as we keep moving, again, getting like positive gradient again now, getting steeper, the steepest it gets to is at this point here where the gradient is exactly 1. And so we can plot that as a point on our derivative graph at +1. And finishing off the cycle, we know that when we get to the end of one cycle, we're back at a maximum for cos x, and that is where the gradient is 0. And so we can plot a point for the gradient at 0. All right, let's get the tangent line out of the way and have a careful look at the points that we've plotted. Well, again, taking some liberties in terms of how they join up. We join those blue lines, and well, we've got, I guess what you would say is another, I mean, you could think of this a few different ways, but the simplest way to think of this blue line would just be this is the graph of sine x, but reflected across the x-axis. So this is just the graph of negative sine x, and it is. So the derivative of cos x is actually negative sine x. Okay, so we've kind of, if we go back over those ideas pretty quickly, and what I might just do is pop the graph of sine x back up there, the original graph that we had, in the black line, and this looks messy with all three of them on there, but let's just kind of summarize it. The derivative of sine x is cos x, and the derivative of cos x is negative sine x. Okay, now obviously we could just say those are the rules and use them, but I think that this graphical approach is a really good idea to take to try to understand why these rules are the way they are instead of just memorizing some rules. Now this isn't really a proper mathematical proof, but it's just an exploration of the graphs, and I hope that you find this helpful. And maybe if you ever sort of forget these rules, you can come back to think about these graphs, and it'll help jog your memory and understand and remember which rule is which. So good luck with differentiating sine and cosine functions, and in the next video we'll go into some specific examples about how we do that algebraically.